Hey guys, so today's lesson is going to be all about force. So we'll go over some diagrams and we'll also talk about how to draw your own force diagrams, do some definitions, that sort of thing. Okay, so for this lesson, we'll go over what different types of forces are, go over some force diagrams. We're also going to look at Newton's 3 laws of motion, and then there's a couple calculations at the very end. So force is a push or pull on an object resulting from the object's interaction with something else. And that could be a direct, like physical interaction, or some other type of force at work that doesn't involve direct contact. Force is always measured in newtons. And you might remember we have seen newtons before already when we were talking about different types of vector quantities. We talked about weight, and weight is also measured in newtons, and that is because it is based on the downward force of gravity. Force, therefore, is also a vector quantity, so it should show both the amount or the magnitude of the force and the direction of the force. There are two main categories of forces. There are contact forces, where one object is in direct physical contact with whatever it is that it's interacting with. And there's at a distance forces, which are forces on an object that result from an interaction between the object and something that it's not actually touching. The different types of contact forces are applied forces. That is, if you actually physically shove something or pull on something. The normal force is just the force of something holding up an object. So right now, the upwards force of my hand that is allowing me to hold this paperweight is the normal force. When I set it on the desk, that is also a normal force that the desk is applying upwards that is stopping the paperweight from just sinking down through it. Friction is also a contact force. So if I were to take something and slide it across the desk, the force of friction would be working against the slide. So if this hair clip was sliding across the desk in this direction, friction would be pushing it backwards and bringing it to a stop. Air resistance is essentially just friction of air molecules against something that is traveling through the air. So you can have air resistance against a plane or a car, or if you hold your hand out the window as you're driving. You'll know that this shaped hand has more air resistance than this shaped hand. You can feel the air resistance. Tension is a force on a string, a wire, or a rope, or something similar to that when you're pulling it tight from both ends. And then spring is if you either stretch or compress a spring or something else that's elastic, like an elastic band. Where you either have to apply a force. So if you were to squish the spring, you would use applied force to squish it, and then the force of the spring pushing outwards on your hand would be the spring force. Same thing, you could pull on the spring using applied force, and then the force of the spring pulling back inwards would be the spring force. And then we only have two at a distance forces, gravitational and magnetic. Gravitational is the force by which massive objects attract other objects towards them. So a massive object, like a planet, attracting other objects to it. So the reason we don't all float off the Earth is because the massive object of the Earth is pulling us all down towards it. And that is what causes weight of all objects that are measured in newtons. And then magnetic forces are either attractive forces or repulsive forces of a magnet on another magnet or on a magnetic object. So I don't know if you guys ever had those magnetic toy trains when you were little, that if you flipped the trains one direction, they would stick together. And if you flipped them in the opposite direction, you could like move one and it would move the other without touching it, because you would have a force of repulsion between those. So opposite magnetic forces attract each other, like magnetic forces repel each other. Forces do always come in pairs of opposites. So for every forwards force, there's a backwards one. For every downwards force, there's an upwards one. And if those opposite forces are balanced, meaning that they're the same strength as one another, the object isn't going to move or change its velocity. So there will be no displacement and no acceleration. If the opposite forces are not balanced, then the object will move and or change its velocity. So it will be displaced and or accelerate. When we draw force diagrams, we are essentially representing all of the different forces on an object. And because force is a vector quantity, we need to represent both the direction of the force and the magnitude of the force. We use arrow direction, so we point arrows to show the direction of the force, and we change the size of the arrows to show the relative amount of force. So larger arrows represent a greater amount of force. So in this diagram here, we have a box or a square or whatever. It is sitting on something, maybe a table, maybe the floor. And because it is not sinking through the table or floor, that means there is a normal force that is pushing upwards from the bottom. Meanwhile, you have gravity pushing downwards from above. If this box was like sitting on some sand and it was actually sinking deeper into the sand as it sat there, that would mean that the gravitational force is bigger than the normal force. And therefore that top arrow would be larger. If on the other hand, it was like slowly floating away like a helium balloon, that would mean that the gravitational force is much smaller than the normal force. In this case, those two are balanced, so it's not sinking or floating. And then we have the applied force, which is in this case, a pushing force, because the arrow is going that direction. And then we also have a friction force. Anytime you have an applied force going in one direction, you will always have either friction or air resistance or both going in the opposite direction. Now this would also be experiencing air resistance, but compared to friction, the air resistance is negligible. So we don't bother writing in air resistance unless it is like in the air and not touching any solid surfaces. So in this case, which direction would this object be moving? So pause, think about it for a second, then come back to the answer. So because the applied arrow is larger than the friction arrow, this object at this point would still be moving forwards. So it would be moving towards where the friction sign is. And then what would happen to the velocity? Well, the velocity would slow down over time. So you would have a decreasing velocity because over time, the applied force would weaken as it's been like longer since you pushed it, and the friction would increase relative to that applied force until the object comes to a stop. So in this case, once again, my gravity and normal forces are balanced, but this time my friction arrow is much larger than the applied arrow. So in this case, the object either would not be moving at all or would have just come to a stop. So if this was just like a refrigerator and I just went up and pushed on it and it didn't move, that would be because the friction between the heavy refrigerator and the floor was greater than my applied force. So that could be an example of what's happening here. Someone is pushing on something and it's not moving. Alternatively, this could be like an after version of the diagram we just saw, where it had been sliding, but at this point, the friction has overcome the applied force and brought the object to a stop. So because of that, you could either say that it's not accelerating at all, or you could say that it just finished a negative acceleration, so slowing down. Okay, next up, we will talk about Newton's laws of motion. So Sir Isaac Newton did come up with 3 different laws of motion to describe force. The first one is called the law of inertia. Essentially what it says is that an object at rest stays at rest and an object in motion stays in motion at a constant velocity unless another force acts on it. So what that means is that the motion of an object will not change unless there is a force on that object. So this is pretty intuitive, but if you have like a pencil case sitting on your desk, it's not going to move anywhere unless you apply a force to it, like if you shove it or something. And then if you have, say, like a ball rolling across the ground, that ball is going to keep rolling and it's not going to slow down unless another force acts on it. And in that case, it would be the force of friction slowing it down. So that does mean that a sliding object would slide forever if forces like friction and air resistance didn't stop it. And obviously if it didn't run into a wall or something. This was actually the opposite of what people used to believe. People originally thought that moving objects would come to rest on their own without any force, and that force was what was needed in order to maintain motion. But then Newton proved that if there is no force, an object will actually keep moving forever on its own, and it is a force that stops the motion. So it is called the law of inertia. So inertia is just the resistance of an object to a change in its movement or its motion. So what that means essentially is the harder it is to move an object that is not moving, the more inertia it has because you're trying to change it from a still object to a moving object, or the harder it is to stop a moving object, the more inertia it has. So force is obviously required anytime you want to change the motion of an object. If you want it to stop or slow down or speed up or start moving, you're going to have to apply some sort of force. The more mass that an object has, the more inertia it has, which again is pretty intuitive. If you think of like, if I rolled a tennis ball across the floor and asked you to stop it, that wouldn't be that difficult to do. But if I rolled a bowling ball across the floor at the same speed, that would be more difficult to stop. I would worry that you would break your foot. So because a bowling ball has more mass, it has more inertia, and therefore it is harder to stop. Because it is moving to change its motion, you would be stopping it. Same thing like if I said, I want you to, shove a water bottle across the floor, that's not going to be that difficult. If I say shove the stove across the floor, that's going to be harder because it has more mass and therefore more inertia. It has more resistance to go from a stop to a movement. And by the way, the more speed something has, the more inertia it has too, which is also intuitive. The faster a transport truck is going, the harder it is for it to stop. And because it has more mass, it's harder to stop a transport truck than like a Mini Cooper. Okay, Newton's second law of motion says that when an object is acted on by unbalanced net forces, it will accelerate in the direction of that force. So that's what we were just talking about with our force diagrams. As soon as we have two areas that aren't the same size, that is representing unbalanced forces. And if our applied force is bigger than our friction force, it is going to move in the direction that that applied force was pushing in. The amount of acceleration, so how quickly it speeds up or starts moving, will be proportional to the amount of force. So more force means it accelerates faster, and it will be inversely proportional to the mass of the object. So more mass means a slower acceleration, which again is all very intuitive. Yeah. Okay, so this is the formula for force. This is a formula that you'll be given. So force is mass times acceleration, or F equals m times a. Like we said before, force is going to be measured in newtons, mass in kilograms or grams, and acceleration in meters per second squared or kilometers per hour squared. So let's try one of these questions. Okay, so we're going to start here with our formula. So force is mass times acceleration. If we have a 60-gram apple that is accelerating at 9.81 meters per second, all we do is multiply those together. And our force would be 588.6 newtons. So try question number 2 on your own and then come back for the answer. Okay, so this time I plugged in the force of 140 newtons and my mass of 12 grams. I'm solving for A. So in order to get the 12 away from it, I need to divide by 12. What I do to one side, I must also do to the other. And that leaves me with 11.6 repeating as my acceleration. And my units would be in meters per second squared. And then Newton's third law of motion says that for every action, there is an equal and opposite reaction, which just has to do with the fact that forces always come in pairs of opposites. And in the absence of motion, those opposite forces will be equal to one another. Okay, that's it for today's lesson.